8.4 Ratios, Similarity, and Probability. Use ratios and proportions to solve problems. Solve problems involving similar figures. Determine the probability of a single event happening. And determine the probability of one or more than one event happening containing an and or. Okay, a ratio is a comparison of two quantities. The ratio of A to B can be expressed as A to B as a fraction, or the words A to B, or a colon in the middle, and that is also A to B. Ratios can be used to solve problems involving similar figures. An equation stating that two ratios are equal is called a proportion. So if you have a ratio and it equals another ratio, and there's an equal sign in the middle, then it's a proportion. Now, usually not all four of those positions, numerator, denominator, are filled. One of them is unknown, but you can set up the proportion to solve for the unknown. So yeah, 12/36 reduces to 1/3. So that's a proportion. 12/36 equals 1/3. The cross products of proportions are equal, and we can use the cross products to solve proportions. So 12 times 3 will equal 1 times 36. Yeah, 12 times 3 is 36. 1 times 3 is 36. So the cross product does equal each other. Now, when we do proportions in a second and we do the cross product, one of those positions is going to be an unknown, and we'll be solving for that unknown. So equality of cross products right here for any numbers A and C and any non-zeros numbers B and D. You just have to make sure the denominators of fractions never equal 0. This ratio equals this ratio, or this proportion is true if and only if the cross product is true. A times D right here has to equal B times C right here. So that's the cross product. Okay, proportions can be used to solve everyday problems and problems involving similar figures. Example 1. The scale on a map shows that 1.5 centimeters represents 200 miles. So that's one ratio I can set up. 1.5 centimeters represents 200 miles. And then if the distance on the map between Los Angeles and San Francisco in California measures 2.9 centimeters, how far apart are the cities? And that's going to be in miles, and that's my unknown. So X miles. So 1.5 centimeters to 200 meters is going to equal 2.9 centimeters to what? We're going to cross multiply. I'm not going to bring the units along. We just need to know that our answer is going to be in miles. 1.5 times X will equal 200 times 2.9. And then to get X alone, divide by 1.5. And X will equal, grab your calculator, do 200 times 2.9 and divide it by 1.5. 200 times 2.9 and divide that by 1.5. And we have 386.667 miles. 386.667, and we know our units have to be miles because the denominator of this one is miles, so the denominator of that one has to be miles. And there's our answer. Example 2. Find the difficult to measure height of a tree by using the tree's shadow and the length of a known object's shadow. So I don't know how tall this tree is, but the proportion of the height of the tree to the shadow it casts will equal the height of a known object to the shadow it casts. These proportions are going to be the same. The ratio of height of tree to shadow will equal the ratio height of something that we know to shadow. We can set up that expression. Height of the tree to its shadow, which is 45 feet, and we're going to get feet on the tree, is going to equal this other ratio, height of the known object to its shadow, 1.75. Now those are all measured in feet, so our answer is going to be in feet. When I do the cross product, I'm not going to bring feet along. I just know that they have to equal feet. The units is feet. So x times 1.75 has to equal 45 times 2. Divide by 1.75. And x will equal that. Put that in your calculator. 45 times 2 divided by 1.75. 45 times 2 divided by 1.75. And the height of the tree is 51.48. I'm sorry, 429. 51.429 feet. 51.429 feet. Okay, when figures have the same shape but are different sizes, just like those two triangles that we just did, they had the same shape at different sizes. They're called similar figures. Two polygons are similar if and only if their corresponding angles are congruent and the measures of their corresponding sides are proportional. This means that we can set up proportions to find unknown side lengths of similar figures. Example 3. And this example right here is directly released from an ACT test. So in the figure below, it says that triangle ABC and DEF are similar. If that's the case, angle A will be congruent to angle D. That angle will be congruent to that angle. So on the ACT, if it asks anything about those angles, they have to be the same measure. Angle B will be congruent to angle E. And angle C will be congruent to angle F. All right, what's the perimeter in meters of DEF, which is this smaller triangle right here? Okay, well, it has to be proportional. The side lengths have to be proportional. So I'm looking for DE right here. DE is X over 5, which is the long side. And that has to equal, okay, DE is going to be similar to the same side to AB. So AB right there is 6 over the longest side of that triangle, which is 10. Cross multiply, and we're going to get 10x equaling 6 times 5, which is 30. Don't know why the numbers aren't staying. And then divide by 10. So x is going to equal 3. So that's a 3. And then it wants the perimeter all the way around this smaller triangle. So 3 plus 3 plus 5. So I have 6 plus 5, and we're looking at 11. So what's the perimeter all the way around? This side is 3, and all the way around is 11. So answer C. Okay, example 4, given the triangle. Now, this triangle has to be similar. Here's why. This side, that side of the triangle, of the bigger triangle, is parallel to this side of the smaller one. So they're cut by a transversal, which means this angle has to equal that angle because those are corresponding angles. This angle has to equal this angle because they're corresponding angles. And that angle equals itself, and it's in both triangles. So we definitely have similar triangles. So we need to find the length of AB. All right. So the length of AB, x plus 11, to the total, this is the full top of the bigger triangle. So full left of the bigger triangle, which is 55 centimeters, has to equal the top of the smaller one, which is 27, to the left side of the smaller one, which is 15. And this is in centimeters, and this is in centimeters. All right, when I cross multiply, I'm not going to bring the centimeters along. I'm going to have x plus 11 times 15 equals 27 times 55. Divide by 15. X plus 11 is then going to equal 5. 15 is 3 times 5. So 5 will go into 55 11 times, and 3 will go into that 9. So that's going to be a 99. And subtract an 11, and X is going to equal 88. And I did this one without a calculator, but you can use a calculator to do 27 times 55 and divide it by 15. Okay, ratios can be used to compare 3 or more numbers. The ratio A to B to C means that the ratio of the first two numbers, A to B, the ratio of the last two numbers is B to C, and the ratio of the first and last number is A to C. So all those ratios will equal each other. In a triangle, the ratio of the measures of 3 sides is this: 8 to 5 to 7. So 3 sides is 8 to 5 to 7, and its perimeter is 240. Well, this is the ratio of sides, 8 to 7 to 5. But if I add those together, 5 plus 7 is 12, plus 8 is 20. That's not 240. Well, when we write ratios, when we write proportions and ratios, we simplify them as far as possible, which means there really was something multiplied on that X, something multiplied on that, 8, something multiplied on that 7, and something multiplied on that 5 that divided out, that simplified to 8, 7 to 5. Okay, so find the measures of each side. Hint, we're going to multiply the X back on, the X back on, and the X back on to represent the measures of the sides. So 8X plus 7X, because we're multiplying the numbers back on that divided out, plus 5X. And with those common numbers multiplied back on, those common numbers that divided out so we could simplify this proportion, this ratio, that then had to equal 240. So we have 20X now equaling 240. Divide by 20, and X is going to equal 12. And now to find all the side lengths, we have 8, and we have to multiply it by 12. That's the number that divided out. We have 7, we have to multiply it by 12, and we have 5 and have to multiply it by 12. So 8 multiplied by 12 is 96, and that's in centimeters. 7 multiplied by 12 is 84, and that's in centimeters. And 5 multiplied by 12 is 60, and that's in centimeters. So that's the measure of the 3 sides. Okay, another ratio that we're going to explore is a probability ratio. So probability compares the number of ways an event can happen to the total number of possible outcomes. It refers to the chance that an event will happen. To determine probability, we need to understand the vocabulary and notation. Event. When we talk about an event, that's the thing we're looking at happening. What's the probability you choose a red sock? What's the probability you get a ham sandwich? So you have to be able to grab the red sock. If there's no red socks in there, then the probability is 0. But that's what we're looking to have happen. The outcome is what happens or could happen, and the sample space is all your possible outcomes, all your possible choices. Okay, the easiest way to calculate the probability of an event is to set up a ratio. So probability, and this is your event. That's the description of your event. So the probability, and then A would say of choosing a red marble or of drawing an ace out of the deck of cards. So probability of A, and that's the event, is the number of ways that we can successfully make that happen out of the sample space. Then we divide by the total number of outcomes. All right, here are some examples of the many ways to represent probability. Okay, a coin lands on its head. The probability that the coin lands on its head is 50%, or 1 out of 2. Now, we should have started at 1 out of 2 because there's one way when you flip a coin, there's one way it can land on its head, but there's two possible ways it can land, heads or tails. So 1/2, or 1 to 2, or 50 to 100, and that just kind of represents, if you did it 100 times, you'd most likely get about a 50 right here, and then 50%. Now, what you need to know right here is it's a conditional it's not a conditional probability, but this is in theory what should happen. So this is a theoretical probability, but if you were to actually take a coin and flip it 100 times, you will rarely get 50 out of the 100 times. It'll be close to 50, but you'll rarely get exactly 50. And if you actually flipped a coin and recorded the number of times that it landed on its head versus landed on its tail, that's known as experimental probability. You actually tried it. All right, so if we write it as a fraction, it can never be bigger than 1. As a decimal, it can never be bigger than 1. And if it's a percent, it's never going to be bigger than 100%. Okay, the complement. So the complement of a probability event. So suppose you need to calculate the probability of an event not happening. This special case is called the complement. The notation for the complement is probability of A and then this little accent mark on the A. And it's read the probability of an event not happening. An event happening and its complement will always add to 1. So if we're asked, what's the probability of this event not happening? Well, you could figure out the probability of it happening and then subtract it from 1. So considering event A getting the flu, the probability that you get the flu is 0.48. How do we calculate the probability of not getting the flu? So the probability of not getting the flu is 1 minus the probability of getting the flu. So 1 minus 0.48 or 0.45. And if we're doing it in percents, it would be 100% minus 48%, which would give you 52%. So as a decimal, 0.52. As a percent, 52%. Okay, example 6. A wallet containing 3 $1 bills, 2 $5 bills, and 5 $10 bills, and 6 $20 bills is found and returned to its owner. The wallet's owner wants to reward the finder with 1 bill drawn randomly from the wallet. Okay, so that's our sample space, is all those bills in the wallet. We have to count up how many there are. So we've got 3 and 2, which is 5, and 5 more, which is 10, and 6 more, which is 16. I'm going to record that out here. 16. So there's 16 bills that you can draw out of that wallet. Okay, what's the probability that the bill drawn is a $20 bill? Well, how many $20 bills are in there? There's 6. So 6 out of 16. So let's put that in our calculator. All right, so 0.375. And that's if you want it as a decimal, but if you want it as a percent, it's 37.5%. Okay, what's the probability that the bill drawn will be more than $5? More than $5 means the $10 bills and the $20 bills. Those are the ones that are more than $5. So I've got 5 $10 bills and 6 $20 bills. So that's 11 out of 16. Put that into your calculator. And we have 0.6875. And as a percent, scoot this over 2 places, so 68.75%. Okay, what's the probability that the bill drawn will not be a $1 bill? Well, let's figure out the probability that it is a $1 bill and then subtract it from 1. So it is a $1 bill is 3. So 3 out of 16 ways we could get a $1 bill. So I have to do 1 subtract 3 out of 16. So 1 subtract 3 out of 16 is actually 13 out of 16. And you could have gotten that by adding these all up. 6 and 5 is 11 and 2 more is 13. So put that into your calculator. And we have 0.8125. And as a percent, that would be 81.25%. Okay, 2 events are independent if the outcome of the first event does not affect and change the outcome of the second event. When calculating probability, it's important to know if these events are independent or dependent. Example 7. A computer class has 18 juniors and 14 sophomores. 2 students will randomly be selected to represent the class on a technology committee at school. What's the probability that a sophomore will be chosen first? Okay, how many total students are there? 18 plus 14 is 32. So there's 32 students. So what's the probability that a sophomore will be chosen? There's 14 sophomores divided by 32 total students. So we can simplify that. 7 out of 16 is the fraction. Calculator. 0.4375 or 43.75%. That's actually a 4. Kind of looks like a 9. Okay, the next one. What's the probability that a junior is chosen first? So a junior being chosen first is 18 out of 36, which reduces to, not out of 36, out of 32, which reduces to 9 out of 16. 9 divided by 16, and we have 0.5625. And as a percent, 56.25%. Now, it didn't mention it, but I'm going to. Those 2 events happening are complementary. So either a sophomore is going to be chosen or a junior is going to be chosen. There's no other way to do it. So down here, what's the probability that a junior is chosen? Well, that's also the same as saying what's the probability that not a sophomore is chosen. So we could have actually gone back up to this first one and just subtracted these numbers from 1. Well, from 1 or from 100%, and we would have gotten these down here. Okay, the next one. If the first student selected is a junior, what's the probability that the second student is going to be a sophomore? Okay, if the first student selected is going to be a junior, then there's no longer 18 juniors, there's 17, but there's no longer 32 students, there's 31. So that junior's been selected. There's 17 juniors left over, but there's 31 students. So now what's the probability that the second student's going to be a sophomore? So now it's going to be 14 over 31 because one of those kids has already been chosen. One of the juniors is already gone. So 31 kids total, not 32. So 14 divided by 31. And we'll round it to 4 decimal places, so 0.4516. Which then if we write it as a percent, 45.16% on that one. Okay, when combining events, the following must be considered when calculating probability. Okay, the fundamental counting principle is the probability of thing 1 times the probability of thing 2. And that's the number of ways that both things can happen. The fundamental counting principle states that if there are p ways to do one thing and q ways to do another thing, then there are p times q ways to do both things. This principle helps determine the sample space for probability. Okay, then dependent and independent events. Two events are dependent if the outcome of the first event affects the outcome of the second event so that the probability is changed. And that's what happened here. So we had taken one of the students. So the probability of the second thing happening was contingent on knowing what happened in the first thing. And that was one student got taken. So the number of students in the class was no longer 32, it was 31. Okay, if the first event does not impact the second event, then they're independent. Okay, combining probabilities where you want both events to happen. So the probability of event A and B happening is the probability that event A happens times the probability that event B happens, but be really careful because they have to be independent. So if they're dependent, then that's going to change this. Okay, multiply the two probabilities together if they're independent. So this is the counting principle right here on example 8. In a school cafeteria, students choose their lunch from 3 sandwiches, 3 soups, 4 salads, and 2 drinks. How many different lunches are possible for a student who wishes to choose exactly 1 sandwich, 1 soup, 1 salad, and 1 drink? Well, there's 3 ways to choose sandwiches. Times there's 3 ways to choose soups. Times there's 4 ways to choose salads. And there's 2 ways to choose drinks. Okay, 3 times 3 is 9. 4 times 2 is 8. Multiply those together, and there are 72 lunch combination. Just combinations. So, combination possibilities. Okay, B. A bag containing 5 red, and 4 white marbles. A marble is drawn from the bag, its color is recorded, and the marble is returned to the bag. The second marble is then drawn. Now, if the marble is returned, they're independent events. The first thing happening doesn't matter. The second thing, it doesn't affect the probability of the second thing. So what's the probability that the first marble is red and the second marble is white? Okay, 5 and 4, there's 9 total marbles in there. So the first one is red, and that's going to be 5 out of 9 ways times, it's an and, so we're going to multiply. Okay, we've put that first marble back in, so there are still 9 marbles in the bag. And then what's the probability the second one is white? That's 4 times 9. So 5 times 4 is 20. 9 times 9 is 81. So 20 divided by 81. And we have, we'll round it to 24.69. Or sorry, 0.2469. 24.69%. Okay, what if the first marble is not replaced? These just became dependent. All right, the first marble is not replaced. So what's the probability that what the first one is red? That's 5 out of 9. But you don't replace. There are no longer 9 marbles in there. There are only 8. So now what's the probability that you get the second marble to be white? Well, there's 4 white marbles in there now out of 8. So we have 20 over 9 times 8 is 72. That simplifies. 4 will go into both of those. 5/18. Put that into your calculator. And 0.2778. 27.78% on that one. Okay, given multiple events, what if you need to determine the probability of either event occurring? So, combining probabilities where you want either event to happen. So, the probability of A or B, we take the probability of A, we add it to the probability of B, but we have to subtract the probability of both of those happening together. Like, what's the probability of both of those happening together? So, beware of overlapping events. Don't count things twice. Add the two probabilities together and subtract any overlap. If there's no overlap, it means the two events are mutually exclusive. Okay, blood types of 150 are shown below. So O62, A67, B15, AB6, add those all up, you're going to get 150. All right. If one person from this study is randomly selected, what's the probability that this person has type A blood? So we have to come over here and figure out how many have type A. And 67 have type A out of total people in the survey, 150. So 67 divided by 150 and 0.4467. 44.67%. Okay, what's the probability that the person has type A, B, and O? Type A, B, and O. Well, you can only have one of these blood types. You can't have both. So that's 0. There's no way you can have both blood types. So the answer to that is 0. It can't happen. And then what's the probability that the person has type A, B, or type A? Okay, AB is right here, and we have 6 out of 150 plus, and these are mutually exclusive because you can't have both blood types. So AB and A, there's 67 out of 150. So add those together, and we're going to get 73 out of 150. Calculator. Um, 0.4867. Or 48.67%. Example 10. You spin a spinner that has 12 equal size sections numbered from 1 to 12. Find each probability that you spin a 3 or a 4. So this is an or, we're going to add them. So I didn't need to write that. We're going to add them. So to spin a 3, there's 1 out of 12 ways to spin a 3. Plus to spin a 4, there's 1 out of 12 ways to spin a 4. Add those together, we get 2 out of 12 ways, which is 1/6. Throw that into your calculator. 0.1667 or 16.67%. Okay, the probability that you spin an even or a 7. Now, these are mutually exclusive because 7's not even. So all your evens are 2, 4, 6, 8, 10, and 12. So there's 6 out of 12 evens, plus there's 1 7, so 1 out of 12. So that's going to be 7 out of 12. Throw that into your calculator. And we have 0.5833. Which is 58.33%. Okay, the probability that you have an even or a multiple of 4. So how many evens are there? There's 6 out of 12. Or a multiple of 4. Well, a multiple of 4 is a 4 and an 8. But aren't those already accounted for in here? So you don't need to do anything. If we did do something, we'd have to add on how many multiples of 4 there were, and that's a 4 and an 8 and a 12. So 3 out of 12, but then we would have to subtract any overlap. And the overlap is the 4, 8, and 12, so 3 out of 12. So they would actually just cancel, and you would have 6 out of 12, which is 1/2, as a decimal, 0.5 as a percent, 50%. All right, the probability you have less than 5, or greater than 9. So your less than 5s are 1, 2, 3, and 4. So there's 4 numbers less than 5 plus greater than 9, and that's 10, 11, and 12. So 3 of those are greater than 12. So that's going to be 7/12. We've already got those numbers right here at 7/12. 0.5833, 58.33%. And I think that's it with study notes 8.4.